So I was sitting on my porch yesterday, just watching an ice cube melt in a glass of lemonade.
Oh, the most exciting spectator sport.
Oh, exactly. I
Yeah.
mean, it's about the most boring thing you can watch, right? It's like watching paint dry, but, wetter.
Right.
But then I started thinking about something I sort of vaguely remember from school
Hmm.
that, the ice cube just sits there floating, and as long as there is still a chunk of ice left, the water doesn't get any warmer. It stays pinned.
A very stubborn little thermal anchor, isn't it?
Right. And in my head, I'm thinking, okay, the sun is beating down on this glass. Heat is pouring into it, but the temperature isn't moving.
Hmm.
And it kind of bothered me because if you put heat into something, it's supposed to get hotter. That's just how the world works.
It's funny you mention that because that exact scenario, the melting ice cube,
Hmm.
is what we might call a glitch in the matrix moment in physics. We gloss over it because we see it every day. But if you strictly follow the definitions of temperature and energy in most textbooks, that ice cube is breaking the law.
See, I knew my high school physics teacher was hiding something. But wait, I remember the explanation for this. I'm pretty sure they called it latent heat.
That's the one.
The idea was that the heat isn't making the molecules faster. It's being used to, cut the ropes holding the ice together.
That is the standard answer. It's what you'll find in almost every single textbook. The energy goes into breaking the bonds, the ropes, as you put it, rather than increasing kinetic energy.
Right.
And since we define temperature as the average kinetic energy of the molecules, the temperature stays flat. Case closed, right?
I mean, it sounds convincing enough. Why shouldn't I believe it?
Well, let's think about what happens when you cut those ropes.
Yeah.
In an ice crystal, molecules are locked in a rigid cage. They can vibrate a bit, but they can't really go anywhere.
Okay.
When you melt that ice, you're turning those molecules loose. They go from being prisoners in a cell to, running around in a liquid.
Okay, so they have way more freedom.
Exactly. If you snap a tether holding a dog back, the dog runs. It moves. Logic dictates that if molecules are freed from a solid lattice, they must be moving more freely.
Yeah?
They must have higher kinetic energy.
Ah, I see where you're going.
Yeah.
If they're moving more freely, they should be faster. And if temperature is speed,
The temperature should
Yeah.
go up, but it doesn't.
so we have a contradiction.
A huge one. Either the molecules aren't actually speeding up, which seems physically impossible when they're changing state, or our definition of temperature is just wrong.
That is a bold claim. You're saying the thermometer is lying or that we're reading it wrong.
I'm saying we might be measuring the wrong thing entirely.
Ah.
So for this deep dive, we're looking at a fascinating paper by Jerry Z. Liu, and his thesis is, it's pretty radical.
Okay.
He argues that temperature is not a measure of kinetic energy. It's not about how fast molecules are banging around.
So if it's not speed, what is it?
He proposes that temperature is actually a measure of radiative energy emitted by the bonds themselves.
Radiative energy.
It's about the potential energy stored in the connections between atoms, not the speed of the atoms themselves.
Okay, my brain is already doing a somersault. Temperature isn't speed. That feels like telling me gravity isn't pulling things down.
I know.
But before we get into the heavy stuff, surely there's evidence that the speed theory works sometimes. I mean, we've built engines and rockets based on this stuff.
And that's the trap. The kinetic theory of gases, the idea that heat equals motion, works incredibly well for some things.
Sometimes.
It works if you're dealing with what we call monatomic gases.
Monatomic, so like lone wolf atoms.
Spot on. Think of helium or argon. Just single atoms floating around, bouncing off each other like billiard balls.
Okay.
If you use the standard kinetic equations to predict how much heat it takes to raise their temperature, this is called specific heat, the prediction is 99% accurate.
Okay, 99% is an A+. If I'm a scientist, I'm popping champagne with that result.
Absolutely. It validates the theory. But, science isn't just about the easy stuff. As soon as you look at polyatomic gases,
Molecules made of many atoms.
right, molecules that are chains of multiple atoms bonded together, the theory just starts to crack. And not like a hairline fracture, it shatters.
Give me an example.
Let's look at octane. You know octane, it's in your gas tank. It's a complex molecule, lots of carbon and hydrogen atoms all bonded together.
Right.
When we use that same kinetic theory to predict octane's specific heat, the error is massive.
How massive are we talking? Like 10% off, 20%,
Try 93% off.
93.
The theory predicts only about 7% of the actual value.
Wait. If my GPS was off by 93% and I was trying to drive to New York, I'd end up in, I don't know, the middle of the Atlantic Ocean.
Or maybe the moon. It's a catastrophic failure of the model. You're pumping heat into the octane, And the kinetic theory says, okay, this heat should be speeding up the molecules. But the temperature doesn't rise nearly as fast as predicted.
There's a huge amount of missing energy.
It's a huge amount that the speed theory just can't account for.
So you're pouring energy in, but it's not showing up as speed. Where is it going?
That is the million-dollar question. And Liu argues it's going into the springs.
The springs.
Imagine the chemical bonds between atoms, not as rigid sticks, but as bouncy little springs. When you add heat to a complex molecule like octane, you aren't just making the whole thing fly across the room faster.
Okay.
You're making those internal springs vibrate and stretch and wiggle.
I can visualize that. It's like throwing a slinky. The slinky moves through the air, but it's also stretching and jiggling all over the place.
Precisely. You are increasing the potential energy of the bonds. And Liu's argument is that this is what temperature actually measures. Not the flight of the slinky, but the stretching of its coils.
But how does a thermometer know how much a bond is stretching? A thermometer is just a glass stick with liquid inside, or a digital probe. It doesn't have tiny eyes looking at atomic springs.
Well, let's think about how we measure temperature in the modern world. Have you ever used one of those infrared thermometers, the little laser guns?
Oh yeah, I use one for my pizza oven. I point the laser at the stone, and it tells me it's 700 degrees.
Right. Does the gun ever touch the pizza stone?
No, I'm standing like 3 feet away.
So how does it know the temperature? It's certainly not measuring the kinetic impact of air molecules hitting it. It's measuring light. Specifically, infrared radiation.
It's reading the heat rays coming off the stone.
Right. And in physics, we have laws like the Stefan Boltzmann law that directly link temperature to the power of that radiation. Or Wien's law, which tells us that as things get hotter, the color of the flame changes.
Yeah.
Red is hot, blue is hotter.
Okay, so color equals temperature.
And color is just a wavelength of light. It's radiation. So Liu connects the dots. We know temperature is measured by radiation. We know radiation comes from the vibration and stretching of charged bonds, that potential energy. Therefore, temperature is a measure of potential energy, not kinetic speed.
Okay, I think I'm with you so far. It makes sense why the speed theory fails for octane. It ignores all the springs. But now we have to talk about the mechanics. The paper introduces some very sci-fi sounding terms.
Yeah, they do sound like something out of a comic book, don't they? Transimpacts and impact trends.
Right. Is transimpact like a transfer of impact?
In a way. But to understand it, we have to zoom in way in. Imagine a single atom. When that atom absorbs energy, heat, or light, what happens to its electrons?
High school chemistry coming back to me. The electrons get excited. They jump up to a higher shell.
Right. They jump to a higher orbital, further from the nucleus.
Right.
Now, what does that do to the size of the atom?
It would make it bigger, I guess, like it's puffing out its chest.
Exactly. The volume expands. Now, imagine this atom is in a crowded elevator. A liquid or a solid. It suddenly puffs up. What happens to the atom standing next to it?
They get shoved.
Violent shoving. This isn't a gentle nudge. This is an explosive increase in electrostatic repulsion. The atom expands, and that repulsive force literally kicks the neighboring atoms away. That sudden physical kick is a transimpact.
So it's like a microscopic popcorn kernel popping. It absorbs heat, pop, and it physically pushes everything around it away.
That's a great analogy. And Liu argues this is the force that actually drives things like Brownian motion.
Brownian motion. Right, that's the pollen thing. You put a grain of pollen in water, look at it under a microscope, and it's just jittering around like it's had way too much coffee.
And the standard explanation is that tiny water molecules are constantly bumping into the pollen grain, nudging it around.
Which seems reasonable.
It does, till you do the math. A pollen grain is massive compared to a water molecule. It's like a cruise ship compared to a dinghy.
Okay.
For a dinghy to bump a cruise ship and make it lurch the way pollen does, that dinghy would need to be moving at incredible speeds.
How fast are we talking?
Liu calculates that the water molecules would need to be moving at about 10% the speed of light to generate that kind of kick from a simple collision.
Okay, if my glass of water had molecules moving at 10% the speed of light, I feel like drinking it would be a very bad idea.
It would be a catastrophic event.
Yeah.
So kinetic collision doesn't really explain it, but a transimpact, that explosive electromagnetic repulsion when an electron jumps, that provides a sharp, powerful force that's much stronger than a simple bump.
That's what's kicking the pollen.
That's the argument. It paints a really violent picture of a simple glass of water.
Yeah.
Just billions of tiny explosions kicking things around.
But you can't just have explosions forever. Energy has to go somewhere else. So that brings us to the reverse process, impact trans.
Yes. Nature loves balance. Impact trans is the process of converting kinetic energy motion back into potential or radiative energy.
Can we get a real-world example of that? Because converting kinetic to radiative sounds a little
It's
abstract.
actually very common. Take a hammer and smash it onto a piece of steel.
Yeah.
Bang.
Done.
Two things happen. First, you leave a dent. Second, if you touch the spot where you hit it, it's hot.
True.
Where did the energy of the swinging hammer go? It stopped moving, so the kinetic energy is gone.
Into the...
Partially. The dent is actually you compressing and stretching the atomic bonds. You've stored energy in the structure. That's potential energy. But you also feel heat. That impact forced the atoms together, distorted their electron clouds, and caused them to release that stress as radiation, as heat.
So the motion of the hammer became the heat in the metal.
Exactly. That is impact trans. Motion turns into bond distortion, which releases radiation. The source paper summarizes this with a dynamic energy equation. Total energy isn't just kinetic. It's the sum of potential, kinetic, and radiative energy, all constantly morphing into one another.
Okay, I think I have the toolkit now. We have springs, we have popcorn kicks or trans impacts, and we have hammer hits, impact trans. Let's go back to the crime scene. The melting ice cube.
Let's solve it.
We established that the old kinetic theory says the temperature should rise because molecules are speeding up, but it doesn't. How does this new radiative bond theory explain the flat line at 0 degrees?
Okay, remember, under this new definition, temperature measures the radiation coming from the springs, the bonds. The more stretched the spring, the more potential energy it holds, and the higher the temperature.
Right. So at negative 20 degrees, the springs are tight. At negative 5 degrees, we've added heat, so they're stretching out.
Correct. But think about a physical spring. Can you stretch it forever?
No, eventually it either gets ruined or it just snaps.
It snaps. There is a maximum limit to how much potential energy a bond can hold. When ice reaches 0 degrees Celsius, those hydrogen bonds are stretched to their absolute limit. They are maxed out.
They hit a ceiling.
A literal energy ceiling. Since the bonds cannot store any more potential energy, they cannot emit any more radiation than what corresponds to 0 degrees.
And since the thermometer is just measuring that radiation?
The thermometer hits the ceiling too. It just stops at 0.
You got it. The so-called latent heat isn't magically disappearing. It's just that the mechanism we use to measure temperature, the radiation from the bonds, has hit its peak for that state of matter.
And what happens to any extra energy you add? It snaps the spring, the bond breaks, the molecule flies off as liquid water.
So the molecules do speed up.
Yes, the kinetic energy does increase, just like common sense suggests it should. The freed water molecules are moving faster than the ice molecules, but the thermometer is blind to it.
Because the thermometer isn't a speedometer, it's checking how stretched the springs are. And the springs are either broken or at max stretch.
Exactly. The ones that break are gone, and the ones remaining in the ice are still stuck at that max stretch. So until all the ice is gone, the average stretch doesn't change.
That is actually really satisfying. It fixes the paradox without needing any magic. It just says, hey, your speedometer is actually a tension meter.
And that's the beauty of it. But, and there's always a but, in physics, this ceiling effect doesn't happen with every single phase change. There is really weird exception that Lou points out.
Which is?
Superfluids.
Oh boy, superfluids. This is liquid helium, right? The stuff that like climbs up walls.
The very same. When helium transitions into a superfluid state, it gets incredibly weird. But here's the kicker. Unlike ice, where the temperature stays flat during the change, with helium, the temperature actually drops while it changes phase.
It gets colder, so the ceiling theory doesn't apply.
It applies, but the mechanism is different. With ice, we're breaking bonds by pulling them apart, stretching the springs until they snap. That's an impact-driven change. But with helium, something else happens.
What's that?
It gets so cold that the electrons actually lose energy and retreat. They fall into orbitals closer to the nucleus.
They tuck themselves in.
Basically. Now, helium atoms are held together by something called London dispersion forces. It's a very, very weak attraction. Think of it like a mild static cling.
Okay, a tenuous connection.
At best. But when those electrons retreat to the lower orbitals, the cling disappears. The attraction vanishes.
So the bond doesn't break because you pulled it. It breaks because the glue just dried up.
Exactly. It's a loss of attraction. Because you aren't fighting against a spring to break it, you aren't pumping energy in to break the bond. The energy state just drops. That's why the temperature falls.
Wow.
It's a bond-limited transition versus an attraction loss transition.
That nuance is incredible. But I know what people are thinking. We've got invisible springs, introverted helium, and popcorn atoms. Is there something I can hold in my hand that proves this? A smoking gun.
There is. And you probably held it in your hands during a ski trip, the reusable hand warmer.
Oh, the ones with the little metal coin inside that you click?
Yes, they're filled with a supersaturated liquid sodium acetate.
I love those things. You click the little metal disc, and it's like magic. The clear liquid instantly turns into a white solid, and it gets super hot.
Let's break that down with our new physics goggles.
Yeah.
You click the disc. That mechanical shock is an impact you're triggering crystallization.
Yeah.
The liquid turns into a solid.
Okay, liquid to solid.
Now think about the molecules. In a liquid, they are sliding past each other. In a solid, they're locked in a crystal cage.
So they're stopping.
Right. The average kinetic energy, the speed is plummeting. The molecules are essentially slamming on the brakes.
Okay, so if temperature equals speed and the speed drops.
The temperature should drop. It should get cold.
But it doesn't. It burns your hands. It gets up to, what, 130 degrees?
Exactly. Kinetic energy goes down, temperature goes up. They are moving in completely opposite directions.
Oh, that's undeniable. You can't argue with a burnt hand.
It is the definitive proof that temperature cannot be kinetic energy. If it were, that hand warmer would freeze, not heat up.
So what's actually heating it? The springs again?
The springs. As the crystal forms, new bonds are created. Those bonds snap into place, and all that stored potential energy is suddenly released as radiation as heat.
It's the perfect reverse of the ice cube.
Precisely. In the ice cube, you put energy in to break bonds. In the hand warmer, bonds form and release energy out. The speed of the molecules is totally irrelevant to the temperature reading.
That really changes how you look at the world. I mean, we learn these laws in school. Temperature is average kinetic energy, and we just nod and pass the test. But a simple hand warmer proves it's fundamentally wrong.
It reminds us that science is a map, not the territory. Our maps, our equations, are approximations. The kinetic theory works great for helium gas, 99% accurate, so we pat ourselves on the back and assumed it worked for everything.
But we just ignored the 93% error on the octane. We ignored the hand warmer.
It's like using a map of New York to navigate London and saying, well, the rivers line up occasionally, so it's fine.
And that leads to the final, somewhat provocative thought from the source material. The author includes a note in his further reading list. Mathematics is not science.
That's fighting words for a physicist.
It is, but what's the point?
The point is, just because you can make an equation balance doesn't mean it describes physical reality. We can force a math equation to fit the ice cube if we add enough constants and factors. But does it explain why?
Probably not. It just covers up the mystery.
Exactly. Real science is about mechanism. It's about understanding the springs, the kicks, the transimpacts, not just fitting a curve to a graph.
Well, I'm never going to look at my lemonade the same way again. It's not just melting. It's a battleground of bond springs maxing out their tension.
And hopefully you won't look at a thermometer the same way either.
Definitely not. It's a potential energy meter from now on. Thanks for walking us through this mind-bending rewrite of thermodynamics.
My pleasure. It's always fun to break the rules a little.
And thanks to all of you for listening. Keep questioning the textbooks, and we'll catch you in the next deep dive.